Today, we're diving into a massive climate problem and a tiny, almost unbelievable hero that might just be the solution. But here's the thing. The answer isn't hiding in some high-tech lab. It's actually out there in the beautiful, boggy landscapes of our planet.
All right, first things first, let's talk about the problem itself, methane. You hear a lot about CO2, but over a century, methane is over 28 times more powerful at trapping heat. It's a real super pollutant, and getting a handle on it is one of the quickest ways we can actually slow down warming in the short term.
So, where is a huge chunk of this stuff coming from? Well, it's not just from the places you might expect, like industry or agriculture. Nope, one of the single largest natural sources on Earth is hiding right out in the open, in ecosystems we usually think of as totally pristine, the world's peatlands and bogs.
Yeah, these incredible, waterlogged landscapes are actually at the heart of the issue. Get this, they cover only about 3% of the Earth's land, but they store something like 30% of all its soil carbon. But they're also massive methane factories. Deep down in the peat, where there's no oxygen, it's the perfect home for methane-producing microbes, which just let the gas bubble right up to the surface.
But here's the twist. What if the solution to the bog's methane problem was already living right there on its surface? I want you to meet the humble sphagnum moss. It's basically the master architect of these entire ecosystems, and, as it turns out, it has a hidden superpower. You see, this moss isn't just sitting there looking pretty, it's an active player in the bog's whole chemical dance. It basically works like a living, breathing biofilter, catching methane before it ever has a chance to escape. So how does this incredible natural technology actually work?
Well, the moss's secret weapon is a microscopic partner. It plays host to these huge colonies of specialized bacteria called methanotrophics, which literally just means methane eaters. What they do is consume methane and turn it into carbon dioxide, which is a way less potent greenhouse gas.
And this is where it gets really cool. It's a perfect symbiotic partnership. The moss creates this ideal home for the bacteria, this watery, oxygen-rich layer that's safe from the oxygen-free peat below. And in return, the bacteria provide the moss with food. The CO2 they release is captured by the moss for photosynthesis, and this whole system is so efficient that up to 30% of the moss's carbon can come directly from the methane processed by its tiny tenants.
So, here's how that biofilter works in real time. Picture it. Methane gas, produced deep in the peat, starts rising up. But before it can hit the atmosphere, bam, it gets intercepted by that top layer of sphagnum moss. And in those little oxygenated pockets, the methanotrophics get to work, neutralizing the gas. This natural filter is so good it can reduce methane emissions by over 90%. Incredible.
All right, so it all seems pretty simple, right? We know this works, so restoring degraded peatlands should be a no-brainer climate solution. But this is where our story takes a really unexpected turn. Nature had a surprise waiting for us.
You know, for peatlands that have been drained and dried out, the logical first step seems obvious. Just re-wet them. Add water, let the sphagnum moss come back and do its methane filtering thing again. Seems perfectly simple, doesn't it?
Well, it's wrong. A major analysis found that just rewetting these landscapes can paradoxically increase methane emissions by a staggering 46%. It turns out adding water supercharges the methane-producing microbes long before the methane-eating moss and its bacterial partners have a chance to get established.
I mean, just look at this. The difference in outcome is literally night and day. The simple approach completely backfires, but a smarter approach, combining that rewetting with removing the nutrient-rich topsoil, basically starves the methane producers while giving the moss a clean slate to grow on. And the result? A stunning 99% reduction in methane emissions.
So that discovery completely changed the game. It paved the way for a much more nuanced and way more effective approach to peatland restoration. It turned a potential climate disaster into a seriously powerful climate solution. It's all about working smarter, not just harder.
So here's what the modern toolkit for smart restoration looks like. 1. You re-wet the land to create the right conditions. 2. You remove that topsoil. And 3, and this is crucial, you don't just wait for the moss to show up, you actively reintroduce it, seeding the area to give that natural biofilter a powerful head start.
And what's really fascinating is that the applications for this don't just stop at wild bogs. There's something called poluticulture, which is basically wet farming of moss, that aims to create productive land that also filters methane. And because the moss is naturally acidic, it can even be used in agriculture. Get this. Adding it to livestock manure has been shown to stop methane production by up to 88%.
Okay, so this powerful science is moving from the lab and research papers into the real world. It's actually being turned into scalable climate action, creating this new, exciting space where ecology and entrepreneurship meet.
Companies are actually popping up to tackle this challenge. Over in the UK, you've got Moss, which has pioneered ways to grow sphagnum moss at a massive scale for restoration projects. And in Germany, a startup called Zukunftsmoor, which translates to future bog, is cultivating moss on rewetted peatlands as a whole climate-friendly business.
But the real challenge here is scale, right? We're now seeing patents for new cultivation techniques, new methods for creating moss seed stocks, and even liquid moss suspensions that can just be sprayed over huge areas by machine. This is the kind of tech we need to deploy nature's solution on a global scale.
So the simple answer, as it turns out, was the wrong one. The truly effective solution wasn't just about hydrology, it was about biology. It required a much deeper understanding of that intricate partnership between the moss and its microbes, and learning how to work with them as nature's own expert architects.
You know, in our search for all these high-tech climate fixes, could it be that some of the most powerful answers have been waiting for us all along in the wisdom of ancient ecosystems? The bog that breathes methane might just be teaching us how to breathe a little easier about our future.